Rao Bhim Chapter 8.4 Cayley-Hamilton Theorem. Definition 8.4.1. We have a polynomial fx and a matrix A. We say that f annihilates the matrix A if fa is equal to 0. Now you have to understand how we are evaluating a polynomial at a particular matrix. This polynomial is just polynomial of a single scalar variable. How are we applying it to a matrix? Suppose the polynomial is 2x squared plus 5x plus 3. In that case, we shall compute fa as 2s squared plus 5a plus 3i. Notice this I. There was no such thing here. You might say it was 3 times 1, and 1 is x to the power 0, so it is a to the power 0. As an example, suppose a is 0, 2, 2, 0, 0, then you can easily check that a square is the 0 matrix. So we can say that fx equal to x squared annihilates a. And of course, I can even take x cube, that also annihilates a. In fact, any multiple of x squared will also annihilate a. Here is the most important theorem of this section, namely Cayley-Hamilton Theorem, which says that suppose I start with a matrix, square matrix A, and I consider its characteristic polynomial, then this characteristic polynomial will annihilate A. This must be equal to 0, and this is the Cayley-Hamilton Theorem. As an example, suppose A is the matrix 1, 2, 3, 4. So let's find out its characteristic polynomial, which is determinant lambda I minus a. That's the definition, and lambda I minus a in this case is this matrix, which turns out to be lambda square minus 5 lambda minus 2. So now if we just compute this polynomial with a in place of lambda, a square minus 5a minus 2i, then you can check that this will be actually equal to the 0 matrix. Now we are going to prove this, but before that, just observe what's the use of Cayley-Hamilton theorem. There's not much use. It's just a fun theorem. So one use is that you can compute its inverse quite easily from this by just taking this 2i on the other side. So it is, you take a times a minus 5i, and that is twice I, so bring that 2 on this side. So you see that a times this is equal to the identity matrix, which means this must be inverse of a. Now of course, for 2 by 2 you do not need all these things, and for higher order thing, finding the characteristic polynomial, doing all the adjustment, etc., that itself takes quite a bit of time. So one cannot say that this is an efficient way of finding the inverse. Now again, if someone asks me to find out a to the power something, say 200, then instead of really raising it to the power 200, we can use this fact by saying that I see that a square is a linear combination of a and I. So a cube is also a linear combination of a and I, because I have got a square equal to 2i plus 5a. Multiply this with a. Once again, you get a cube. This is your a and this is a square. But I already know that a square can be expressed as a linear combination of I and a. So this is again a linear combination of I and a. If you multiply this further with another a, you still remain a linear combination of I and a, because every time you get a square, you replace that by 2i plus 5a. In this way, all powers of a are nothing but linear combinations of I and a. So if you want to compute this high power, you just evaluate a linear combination of a and I. And again, this is not the most straightforward way, because you have to do this thing and figure out the coefficients, and that in a sense will force you to go through basically the same computation as computing it explicitly. So I cannot say that Cayley-Hamilton theorem is a terribly useful theorem, but it's definitely a very elegant theorem. Now here is a naive but wrong way of trying to prove it. We have chi a, this characteristic polynomial given by this, so you might be tempted to just replace this lambda by a and conclude, a times I, and hence conclude this is 0, determinant of 0 matrix is 0, hence done. That is not correct because of a number of things. Number one, if you really do this, remember determinant of this is just a number, while as this is a matrix. So a matrix cannot be equal to a number. So this result just simply cannot be true. This 0 is a matrix 0. But if you try to do it, you will get scalar 0. The second thing is that it does not really make sense, because what am I doing here? It is lambda minus all the diagonal entries. Now you cannot say matrix minus all the diagonal entries. That will not remain an overall matrix. Only the diagonal things will be all undefined quantities. So you cannot prove it like that, though this looks like notationally an appealing way, and it does give something very similar to that, but that's not the correct proof. The proof that is given in Rao Bhim Chapter is a typical Rao Bhim Chapter proof, rather complex. So I will give you the more standard proof, and this uses the theorem that A times the adjugate of A is determinant of A times I. Now we all use this when we compute inverse. So let's just quickly recall how you compute this thing, A, B, C, D, say. When we compute inverse, we all know this formula. We have to divide by the determinant, AD minus BC, and then we do something funny here. What we do is we swap them, we put D here and A here, we keep them in their place, but we just negate them. Now, what are we doing here? What we are doing here is basically computing what is called the adjugate. Sometimes it is called the adjoint, but that terminology is deprecated, not used anymore. We call it adjugate. So, adjugate of this matrix is this. Now, what does adjugate do? Adjugate does the following. If your original matrix is n by n, this matrix is also another n by n matrix, and in order to find out its ith entry, you look at this entry and you strike out everything in its row and in its column. Whatever remains, in general it will be an n minus 1 by n minus 1 matrix. Take its determinant and put it there together with a sign, and the sign is determined in the following way. You consider which particular entry you are finding. In my case, it is the 1/1th entry. So you find 1 plus 1. If this number is even, then you take the sign to be 1. If this number is odd, then you take the sign to be minus 1. So basically we are doing minus 1 to the power that thing. So I am sure you already know about adjugate, so I just quickly reminded you about that. And why do I have this result? Because of the fact this result, which is due to Jacobi, he says that A times adjugate will always be a multiple of the identity matrix, the multiple being determinant of A. As a result, if determinant is non-zero, in that case you can divide by it and get a matrix such that A times this by determinant is identity, which means that matrix is inverse of A. So that is basically why this formula works. So this is a very standard result, frequently used result, and we are going to make use of this in order to prove the Cayley-Hamilton theorem. So by that theorem, we get this. Instead of A, I am working with lambda I minus A times its adjugate will be its determinant times identity. Now, quickly understand what type of matrix this is. Every element of lambda I minus A is of the form either a number that comes from A, or it is something like A minus A11 like this. So either it's a number or it's something to do with lambda. So when you are doing this adjugate, what are you doing? You are taking some particular entry, striking out its row and column and working out the determinant of the remaining n minus 1 by n minus 1 submatrix. Now, in those things you have got at most n minus 1 many terms with lambda, because there is no lambda square anywhere. Every term is either has lambda degree 1 or lambda degree 0, no lambda at all. So in all the terms of that determinant, you can have at most n minus 1 lambdas multiplied together. So all the things must have degree at most n minus 1. So every entry of this matrix must be a polynomial in lambda of degree less than or equal to n minus 1. So just to fix up ideas, let's take one hypothetical example. So suppose A is a 3 by 3 matrix, then adjugate of lambda I minus A will be a typical matrix like this. I am not saying this really occurs for any matrix. I just wrote down certain polynomials of degree less than or equal to 2. So every entry is a polynomial of degree less than or equal to 2. So let's just get rid of this square here. Now what I am going to do is I am going to collect all my lambda square terms together to get something like this. So I have a lambda square with coefficient 1, I get this, no lambda square, so I get 0, no lambda square, I get 0, then no lambda square, I have 1 lambda square, I have 2 lambda square. By the way, this is actually not possible because all my things are just lambda minus something. You will never get a coefficient of lambda square other than 1 or 0. So it should be 1. Similarly, this has 1 lambda square, this has 1 and this has another. So it is this matrix times lambda square which captures all the lambda square terms here. Now similarly, if I take all the lambda terms, you get another 3 by 3 matrix times lambda plus all the constant terms, so you get another constant matrix. So I can write this adjugate of lambda I minus A as what is called a matrix polynomial, namely a polynomial in the scalar variable lambda, but the coefficients are actually matrices. So I can express this adjugate as a polynomial of degree n minus 1 at most, where in fact it will be of degree n minus 1. It is some coefficient matrix, I call it hn minus 1, then I have hn minus 2, going on all the way up to h naught. So there are no lambdas inside my H matrices. They are completely given by suitable combinations of elements of A. Now similarly on the other side, I have this, which is nothing but the characteristic polynomial times the identity matrix. So if I write down my characteristic polynomial, which is just this thing, as again this is something which is of degree n, so I write it as lambda to the power n plus something which I call say a n minus 1 lambda to the power n minus 1, working all the way up to a naught, then this times the identity matrix. So this will be equal to, this times this will be equal to this, and I am going to equate coefficients of lambda. Lambda minus a times, this is my adjugate, equal to determinant times identity. I have written both the sides as polynomial in lambda. So now I am going to do the multiplication. So let's understand how do I get lambda to the power n term here. It is this lambda times this. That is the only way I can get lambda to the power n. So immediately I can say that hn minus 1 must be equal to identity by equating coefficients of lambda to the power n. Now if you feel uncomfortable about equating coefficients, a technique that you have learned for scalar coefficients, does that still hold for matrix coefficients? Don't worry, because what we are doing is simply we are using the scalar valued equation matching for each of the entries separately. That's all, and just writing them together. So I am not really using any new result. So this is for the power lambda to the power n. Now let us see how we can get the power lambda to the power n minus 1. Now there are two ways. I can multiply this with this, or I can multiply this lambda with the next term, which is lambda to the power n minus 2. If I multiply this with this, I will get identity multiplying hn minus 2 and minus a multiplying hn minus 1, and that must be equal to the coefficient of lambda to the power n minus 1 here. Now you can see the pattern. This pattern will go all the way, so the next thing will be n minus 3 minus a hn minus 2 equal to an minus 2 identity, and so on. Now we have to worry about how we can get the constant term. Now the constant term may be obtained in only one way, namely by multiplying this minus a with this h naught. So the very last one, just like the very first one, are somewhat different. They have only one part, and these intermediate things will all behave in this way. Now what follows is the really fun part. What you do is, you just remember that these are the coefficients of my characteristic polynomial. Now what are we trying to prove? I am trying to show that the characteristic polynomial evaluated at A must give you 0 matrix, which means I am really trying to find the following: A0 I plus A1 A plus A2 A squared, etc., will be equal to 0. Well, you have all the coefficients here, so now I would suggest you leave this unaltered. A0i is A0i. You need A1a. You multiply this with a from the left, the way I have written. You multiply this with a, this equation. Similarly, you multiply this one with a square, etc. So basically you want to get characteristic polynomial evaluated at a on this side. Now what happens? If I multiply this with a, you have an a here, and you have an a square here, and this becomes a. Now the moment you add, you see that this and this just nicely cancel out. Once you multiply the preceding one with a square, similarly this and this cancels off, and you get cancel, cancel, cancel. Finally everything telescopes out, and you will be left with, on this side you will be left with characteristic polynomial of a evaluated at a. On this side you will be left with nothing, so you will get the 0 matrix. So that is one way of proving the Cayley-Hamilton theorem. This is not the proof given in Rao Bhim Chapter, but this I think is a more elegant way of proving it.